Hi, so in this video I'm going to show you how to use multiprocessing pools to spread CPU-bound workloads across multiple cores on your machine. Now, as usual, all this is available in the repo. You have the README file that basically explains what I'm going to discuss here in the video, and then you have all the example code as well. Link to the repo is located below. So one thing to note, as I mentioned before in this channel, is that for IO-bound workloads, a much better alternative is to use async IO or even threading. And I give you the link to the video in the notes here. So let's look at the first example and we'll jump directly into code. So we need a long-running function, right? And we essentially are going to want to call multiple of these functions. I'm going to call those jobs. And then we're going to want to spread the load across multiple CPUs, multiple cores. Now, as you know, Python is single-threaded. So doing multi-threading or doing async IO doesn't help when it comes to CPU-bound workloads. It works just fine when we have IO-bound workloads, but it doesn't work when you really want to get more computational power out of your machine. And of course, Python, by default, really doesn't handle that. Now, I've also discussed in the past, and I've also got a link to that video in the notebook here that you'll find in the repo. I've also discussed that when I work in more larger production environments, I never bother with multiprocessing. Why? Because multiprocessing only scales to one machine. And really, when I look at the scale of the problems that I have to work on, one machine isn't sufficient necessarily. I want to be able to scale that across multiple machines. So I take a very different approach and I do more of a distributed kind of computing where I have a queue server like maybe Redis or maybe SQS or ElasticMQ or RabbitMQ or whatever you want. And then I have these different Python workers that simply grab an item from the queue and then do the work based on the data that's basically the arguments, you can think of it, the arguments that the function needs to run. That's what the worker does. It grabs it from the queue. This is very different. We're going to do that from our Python main code, and it will only scale to the number of CPUs or cores that you have on your machine. So we need these long-running functions, right, that are computationally intensive. And I'm going to use a blocking sleep call to simulate a CPU-bound function. A lot of the examples I see everywhere on the web uses that, so let's give it a shot, or should we? Well, let's just do it first and see what happens. So this function is going to be simple. I'm going to show you a function where we can pass positional arguments. So this function is going to take two positional arguments. It will sleep a certain amount of time, and it will return the sum of those two values. We are going to want to run this function a certain number of times with different input values, and then we'll want to spread this computational workload across multiple cores. So we need to spawn multiple parallel processes. This isn't just concurrent now, this is also parallel. We need to be able to pass values to the function, and we also need to get the results back. Okay, so let's go ahead and see how we're going to do that. All right, so first off, I'm going to use Python 3.12 here. And the first thing we're going to want to do is to import, from multiprocessing, we're going to import the pool object. Now, I'm also going to do random sleeps and things like that. I'm also going to do random arguments to the function we're going to call. So I'm going to want to import from random. I'm going to import randint. And I want repeatable results, so I will actually seed the random generator as well. So I'll import that. And then from time, I want to import perf counter. We're going to use that to time how many things, how long things are taking to run. And then I'm also going to import sleep, which is a blocking call, remember. And we'll use that to basically simulate a long-running function. So let's go ahead and write our long-running function. It's going to get an ID, which I'm going to call the job ID. Remember, I'm going to call this function multiple times, and I'm going to give a number to each call, essentially. That's going to be the job ID. Then it's going to need to take two arguments. Let's just call them arg1 and arg2. And then I'm also going to pass in the amount of time that I want this function to sleep. And then we'll start by essentially just printing out what's happening right now. So we'll say running job, and let's call it job number, job ID, and then we'll say what the sleep is. The sleep is the sleep time, okay? So that should be our first statement. Then we actually are going to sleep, right? So this is what everybody uses on the web, I've noticed, to simulate a long-running function. So finished running a job, and then I'm also going to repeat here the job ID, because once we start doing this parallel processing, we need to know which one finished, right? Things are not going to happen sequentially, so we'll need to know. And then last, I'm going to return some value, and in this case, I'm just going to return the sum of the two arguments. So now I need another function that I'm going to use to run this, to basically call this long-running function multiple times using a multiprocessing pool. So let's go ahead and write this function, run pool, and I'll use two variables here, two arguments, one job size and pool size. Job size is going to be how many calls do I want to make to this function, and the pool size is, well, how much concurrency do I want? Essentially, you can control the size of the multiprocessing pool. This is going to do that. And then I'll call this run pool with whatever values I want for job size and pool size. So the first thing I need to do is I need to basically build up all the arguments that I'm going to need to call this long-running function. And I want to basically create multiple sets of these arguments. So I'm going to do that here, where I'm going to say for I in range, and then we'll say job size, okay? So we're going to iterate through that. This means we are going to create that many jobs. What do I need for each job? Well, I need the job ID, which I'm just going to make I, right? That's just going to be that. I need some arguments. So I'm going to pass a rand int, let's say between 1 and 100. And then we'll do a rand int between 1 and 100 for arg2. And then we need the sleep time. And here I'm going to sleep between 1 and 3 seconds. Now you might be wondering, why am I not doing that inside the long-running function? Well, you're going to see when we call this eventually, these are going to start running individually, right? Possibly in parallel. And I want things to be repeatable. Since I don't know the order in which those functions are going to start running, I want to have a repeatable result, which means every time I call this function, this third function, I want it to always have the same sleep. And that's just so I can compare things when I start increasing the pool size. So that's the only reason I'm doing it this way here. All right, so now we've got the jobs, right? Those are the jobs. And now we need to kick off all those processes. And we're going to use the pool. Now, pool is a context manager. And it can take an argument called processes. And that's just our pool size. So we're telling it how many processes we want. And then we'll get a pool instance object back. So that is our context manager. And what I want to do is I want to call this function, long-running function, passing it these. Now, if you don't know the map function and the star map function, you should go and take a look at it in the functools module, because this is essentially the same thing, right? Here we have a tuple of values, but this doesn't expect a tuple of values. It wants that tuple essentially spread out, right? And so we're going to do that by using the star map function. Now, we can't use the actual star map function in the functools module, but the pool object gives us a star map. And we only use star map because we essentially have multiple of these things, multiple arguments in a tuple. So we need to star map it. If we had a single value, then we could just use a plain .map. Pool also supports that. And I'll show you that later. So let's do a pool style map. And we're going to long running function. This is the function that we want. And we're going to pass it jobs, right? So we're going to essentially apply long running func to every element of jobs. But because we have the style map, it's going to essentially expand this into positional arguments for long running func. All right, and that's all we need to do. Now, once the context manager exits, then the pool essentially is closed. And at this point, we can now get all our results. So this context manager is not going to exit until everything is run. So here, we're going to get regular results. Now, where are we going to get the results? Well, we get that as the result of the pool style map. So we can call this all results. So when the context manager exits, all results will have everything. We'll have the results from the individual calls. So we can say for result in all results, and we'll just print the result, which is just going to be the sums basically of the arguments. All right, and that's it. That's how simple it is to set up multiprocessing with a pool. Now, let's go ahead and write our main code. So if we're running this as the main module, then we're going to start, set that equal to perf counter. Then we're going to seed to 0, just so that we have now, a repeatable random generator now in Python. And we're going to run the pool. So we're going to call run pool, and we're going to give it job size, let's say equal to 50, and then the pool size. So I'm going to start with a pool size of 1. This means that we should only get one function essentially executing at a time. That's the pool size. Essentially what we're doing here is linearizing the execution of all these functions. It'd be no different than just basically calling, long-running function on each job in a loop, waiting till each one finishes until the loop, continues until we get all our results. That's essentially what this is doing here. And so once we're done, I'm going to print the elapsed time because I want to see the elapsed time based on the pool size. So elapsed time, and it will be perf counter minus start, and then we'll do a minus start colon.2f. Okay, like so. All right, that's it. So let me go ahead and run this. Let's see if we have any issues. Actually, I can just run it this way. I can run the example 1. All right, and as you can see, basically the way it's running, each function call, right, the job is running, then it finishes, then the next job starts, and so on. So I have 50 of those. It's going to take a little while, so I'll pause the recording and resume when it's finished. Actually, while this is running, I want to show you what's happening to my CPU. So you can see, so I'm running on a Mac. I've got an M1 Mac, so it's got 10 cores. And I've basically restricted this to just the Python processes. But you can see the CPU load. The CPU load is irrespective of the filter that I have here. The CPU load is not very high. Right, we're running at about, we've got 80%, 87% idle. All right, so it's finished running. We're now at, 84. It's doing, my computer obviously is doing work in the background as well. But you can see how long it took to run, 96 seconds. So now let's go ahead and change our main call, and let's set the pool size to 2. Now remember this number. We had 96 seconds. I'm going to write it down. And now I'm going to run this again. So now you can see it's running, multiple jobs. You'll notice one thing as well. We no longer have any kind of say on the sequence in which the functions are being called. So that's very important to understand. And this is typical of concurrency, right? And typically in concurrency, and I have a video that talks about concurrency concepts, we usually do not want to require certain sequential aspects of the code, right? They need to be able to be done in parallel and in any particular order and still arrive at the same result. Now let's see what's happening to our CPU. So you can see that it's really not doing much. It's pretty stable. If I unfilter and show you the top, right? PyCharm, okay, it finished, but it really, my computer really wasn't breaking a sweat. But you can see now that it took 54 seconds. So we went from 96 seconds to 54 seconds. And we can keep increasing this. Let's say that I have, I've got 10 cores. And let me go ahead, and usually what I do is I don't want to swamp my system because I want to be able to, maybe open a browser or read an email while something is running. So I don't try and use all the cores on my system. I've got 10 cores, I'm going to use 8. And let's see what happens. So now I'm going to run this again. So as you can see, it's running. Now, as you can see, the CPU is starting to creep up a little bit. You can also look at the CPU over here, which is maybe, a better view of what's going on. But it's still not really doing much, which is surprising, right? I'm using all 10 cores. What's going on? All right, well, let's continue. Let's set the pool size equal to, all right, I'll set it to 20. I only have 10 cores. I'm going to try and run it 20 concurrently. Now, obviously, it's not going to do 20 in parallel. It can't. There's only 10 cores. But it's going to schedule basically more than one per core. And let's see what happens now to this timing. So now we're at 1510. Let's go ahead and run it with a pool size of 20. So there we go. It's running. And if we look again at the CPU, you can see that it's still not breaking a sweat. And now we completed in 6 seconds. So you can see the difference, right? When we did the linearized version, it took 96 seconds to run. Now it's taking 6 seconds to run. All right, can I make this better? Can I set this maybe to 50? Let's see what happens. So again, just want to point out that the CPU really isn't doing much. It's still pretty much, what it was before. And it took 3 seconds to run. So this is kind of weird, right? What's going on? I mean, I'm running more than cores that I have. Why should it be running faster and faster and faster? And the issue is this. This is a long-running function. So if we go back to the code, this is a long-running function. What is it doing here? It's sleeping, right? This is kind of the common, the kind of the internet wisdom here is that to mimic a CPU-bound function, we use a sleep. Well, that's totally bogus. Because sleep just does nothing. So that's why we never saw the CPU actually spike. We're not taxing the CPU. So it makes sense that we can increase our pool size more and more since each CPU now receives more than one function to run. Well, since one is sleeping, the CPU has time to process the other function that has been scheduled to run on that core, right? And this is why we're seeing this kind of result. So I've got that in the notebook. I talk about it here. I have some experiments where I show you the numbers. And so that's the problem, right? Sleep does not simulate a CPU-bound workload. So much for collective wisdom, right? In this case, it's okay. I was able to show you how to write basically code that uses multiprocessing here, right? But it's really not making the point of the pool size the way that we really want to. This should be a CPU-bound function, right? So this is not going to be a good example. So instead, I'm going to actually implement a function which actually does tax the CPU. So that's going to be example number 2. So let's go ahead and call it example2.py. So I need a long-running function. Now that's in the notebook that is linked below. I'm just going to copy-paste it here. And basically, it's something called the sieve of Aristophanes. It's basically a way to generate prime numbers. You don't have to understand the algorithm. Basically, it's just doing a lot of computations. All right? So now I'm going to want to do the same thing as before. So I'm going to take this run pool. Actually, I'm going to take the whole thing here that we had, because all I'm changing now is the function that I'm going to call, right? So now I'm not calling a long-running function anymore. I'm going to call sieve. Now sieve only requires a single value. It doesn't require anything else. I'm not going to put in the job ID and that kind of stuff. So this means that my job now is no longer a tuple. It's just going to be a random integer. Now I want this to be computationally intensive, so I'm going to make a random number between 1 million and 10 million. So when I pass, let's say, a number 1 million to the sieve, it's going to identify all the prime numbers that are less than 1 million. If I pass 10 million, it's going to identify all the prime numbers that are less than 10 million. Now you'll notice there's a slight difference here. I no longer have a tuple because this only needs a single variable. If you look here, we had multiple variables, we had a tuple, and then I said this is why we had to use the star map to essentially explode the tuple into the arguments that are needed for the long-running function. Here, I've only got one. So we don't use star map because this is not a tuple, this is a single value that's going to get passed to sieve. We use just map, right? That's all we need to do. So I'm going to do something a little bit different for the result. I certainly do not want to print all these prime numbers again and again and again. But what I'm going to do basically is I'm going to print all results 0. I'll print the result of the first one just to show you that it returned prime numbers. And then for all result in results, I'm just going to say print, let's say, number of primes found, and I'll make that the length, right, of the result. Again, this is just to see that data is coming back for all the calls that we made, but I don't want to print each one out. Okay, so now what do I want to do? Well, I want to do the same thing. When I'm going to do those, I'm going to change my job size to 100. So I'm going to want to run 100 of these computations. And initially, I'm going to set a pool size of 1. Again, just as a base starting point for if we were doing these computations. So now we've got a CPU-bound workload, right? The sieve is a CPU-intensive piece of code. It's not sleeping. It's actually using the CPU actively. So with pool size equal to 1, we're going to see how long would it take if we were to run all this just linearly. So let's go ahead and run now example 2. And I'm going to make this a little bit smaller so that we can also view the activity monitor here. And I'll go back and just restrict to Python. And then we'll see also up here what's going on. But anyways, let me go ahead and run this with a pool size of 1. So run example 2. Now you can see it's running the sieve. And you can see that we don't have, overall, we don't have a huge spike in the CPU, right? One of the CPUs basically is doing work right now, and the other ones are doing whatever else they do normally. So I'm going to pause the recording and then come back once it's actually finished, because this is going to take a while to run. All right, so it finished running. You can see that our CPU is basically the same it was before, right? Not a whole lot of changes. And it took 56 seconds, 57 seconds if we round that, right? So this was with a pool size of 1. Now let's go ahead and change this to a pool size of 2, just 2. Let's go ahead and run this, and let's see what's happening with our CPUs. So again, my computer isn't really breaking much of a sweat. If I bring the activity monitor back, you can see though that the idle time is down to about 64. And I'm sorry, this is small to see. I can't increase the font size. Take my word for it, this says 64, 67. So definitely we're using now a little bit more of the CPU, right? Sometimes it goes to 30 idle, 47 idle. So it's kind of bouncing around a little bit. But you can see overall, we're using a little bit more of the CPU. And in fact, you can see now that it took 32 seconds, right? Which is as we would expect. We're running two processes in parallel. We would expect that as long as our computer can handle it, it's going to give us, a faster response, a faster result. Okay, let's switch the pool size to 4. So we went from 57 seconds to 32 seconds. Now let's run it with a pool size of 4. And let's see what's happening with our CPUs. You can see now that they are starting to really spike up. You can see that graph at the top, right? Or this graph over here. You can see that it's spiking quite a bit more. Our idle now was down to 30, right? And it took 17 seconds to run. Okay, so that's great. It's running faster and faster. So I've got 10 cores. I'm going to change this to 8 just so I don't swamp my computer. And I'm going to rerun this again. And we'll see that now we're certainly spiking the CPU quite a bit more, right? You can see that we have this much bigger spike in the CPU. Same thing over here. And now it finished running. So now things are coming back down to normal. And it took 11 seconds to run. So we went from 57 seconds, if we had written this code to be just linear, to now 11 seconds by being able to leverage multiple CPUs on one machine, right? Now, let's keep going, because if you remember with the last example, we could keep going up and up and up and up, and things kept getting better and better. Well, that was again because, conventional wisdom of oversimplifying things on the internet to make, quicker examples or quicker videos. I don't know what the reasoning is, but doing a sleep isn't representative of a CPU-bound workload. Here it is. So let's see. I'm going to swamp my machine. I'm going to go up to 10, and let's see what happens. So now again, we're getting this spike, right? So you can see my idle time is 0%, right? That means I'm really swamping my machine. There's not much, work that I can do on this machine while this is running. However, it took 10 seconds. So it was a little faster than the one with 8 cores. Okay, let's keep increasing the pool size. Let's go to 20 and let's see what happens. So again, we're going to be spiking our CPU, as you can see, right? And that's because we have CPU intensive work being done by each core, but we only have 10 cores. So it doesn't matter if I have a pool size of 20, the function that's running currently on the core has to finish before the next one can run. So I'm limited to really 10 at a time if you think about it. And in this case, you can see my elapsed time is still 10 seconds. That hasn't changed, right? I could jack this up to 50 and the same thing is going to happen. We're going to see that, yes, it's scheduling all these things 50 at a time, but the CPU can only, the machine can only handle 10 at a time. So yes, it basically, pins my CPU entirely on this machine. And again, we still have an execution time of 10 seconds. Nothing's changed. Okay, so I discussed that in this, in the notebook, in the notes that I have here, I talk about it. All right, so that's really the basics of using a multiprocessing pool. We can use this very, very simple context manager to set things up. Now, I do want to show you one more example, and this is how to pass named arguments when you spawn your processes. As we saw with the map or the style map, you can pass positional arguments, but not named arguments. Now, there are various techniques that you can use to work your way around it. If you control the function that's being called, you could rewrite it so that it takes only positional arguments. If you don't have control in that function, what some people do, they'll write a wrapper function that takes positional arguments only, and then creates, makes the call to the actual function, passing in the named arguments as necessary. So those work, and again, I see that mentioned everywhere. I think one person comes up with that idea, and then everybody just, goes on the bandwagon and just copies that. But we don't need to do that. There is another way of running multiple processes in a pool, but not using this map or this star map thing. Instead, we have to use an apply. Now, there's actually an apply method, and the apply method allows us to launch one function with a set of arguments, and we can pass positional and named arguments that way. The problem is that apply is a synchronous call, so it will not actually return until it's finished running. Now here we want to run things in parallel, so it's basically useless for us. We need to be able to spawn the worker to call the function and then have our code immediately come back while the function is still running so that we can, kick off the second one and the third one and the fourth one. And so for that, we have an apply async method. And this async method is basically going to return something that's going to be what's called a future. And I'm not going to get into that here, but basically it's going to return an object that will eventually contain the results of that function running. But it returns control to our code immediately. So the easiest is for me to just show you how that works. So let's go ahead and create example 3. So this is basically another way of launching things. So I'm going to take this code and probably should spell things correctly, or at least in a way that's PEP compliant. So I've got the same imports as before, nothing's changed. This is still my Aristophanes sieve, right? Nothing's changed here. I have the upper bound, but upper bound you can see now requires to be passed in as a named argument. And then for good measure, I threw in 2 positional arguments as well, which really do nothing. And then the job ID as well, that needs to be passed in as a named argument. So all these things are just extra, parameters that I don't really need for this function, but I want to show you how we can call this, right, from our pool. So it needs 2 positionals and 2 keyword-only arguments. All right, so let's define run pool. And again, we're going to have job size and pool size. Okay, nothing changes here. Now, I have to create my jobs. So I have to create my parameters, right? So I need 2 kinds of parameters now. I need positional and I need named arguments. So I'm going to create a tuple, and that tuple is going to contain, in its first thing, it's going to contain the positional arguments. So I'm going to pass in I and I plus 1, and this is basically for I in range job size, right? Just like before, we're going to create that many jobs. Now, this is going to be my positional arguments that I'm going to pass to function. I also need the keyword arguments. How do I pass keyword arguments? Well, I'm going to set up a dictionary, and I'm going to call it upper bound. So that name has to match the name of the parameter here. And upper bound, and let me put that over multiple lines. So upper bound is going to be rand, let's do rand int, and then we were doing 1 million to 10 million, just like before. And I also need the job ID. So just to show you that I don't have to specify them in the same order, I'll specify the job ID first. So the job ID, I'm just going to make that equal to I, like so. Okay. And this is why I'm getting all the squiggles. All right. So this now is essentially the arguments that I'm going to need to call when I call this function. So now I'm not going to use a context manager because I need to be able to work with the pool that with the context manager, when you exit the context manager, everything kind of shuts down. The pool is closed and the pool is, is basically terminated. I do not want that. I want to be able to create my pool, kick off all the functions, close the pool, and then, just like we have with threading, and I've got examples of that in this channel as well, we want to join the pool. What the join does, just like with multi-threading, it basically waits until everything's completed, everything's finished running, right? So that's kind of what we're going to do here. So I'm going to create my pool, and I'm going to processes equals pool size. This is no different than before. But I'm not using the context manager. Now, I'm going to get these asynchronous results back. So let's call it async results, just before we had results, because it was kind of synchronizing things. It was doing the join inside the context manager. Here I'm doing this manually. So what do I want to do? Well, I'm going to iterate through the jobs, right? What am I going to grab? I'm going to grab the positionals and I'm going to grab the keyword arguments. So I'm going to call this positionals, comma, keyword args in jobs. So basically, I'm unpacking the tuple here into positional and KW args, keyword args. And what do I want to do? Well, I want to do pool.apply sync, right? So I want the, async. I want the apply async. I don't want the apply because that would block. I want the apply async. And I'm going to apply what? Well, I'm going to use the function called func. And I'm going to pass it arguments, which are the positional arguments. So it's the arguments here is expecting a tuple containing all the positional arguments in the correct order. And then I have another argument here that I can use called keywords, KWDS. And that expects a dictionary with the named arguments. Well, that's exactly what KWArgs is, like so. Now, because I'm doing apply sync, this thing is going to run to completion before any of the functions have completed. And then each one is going to return an async result instance. And so this is going to be essentially what my list is here. It's going to be a list of async results. But the results haven't come back yet. They're still in the process of being calculated. So now what I need to do, I need to indicate to Python that I'm done adding things to the pool. So to do that, we do a pool close. And now I need to wait for the async results to come back. Remember, my code is still running now. Yes, I've got things that are basically asynchronously going to get pushed off to different CPUs, and the results will eventually come back, but this code is still running. I want to get to the actual results. If I was to try and print the results right here, you would see that I would get these async result objects back. I wouldn't get the actual result. So what I need to do is I need to wait for everything to finish. And this is when we do pool.join. And now at this point, the code is going to block until all of this has finished running, until all these functions have finished running. Once it's done, then I can look at every result that's in this list. Now that result isn't going to be the original result, this primes. It's going to be, remember, the result is this, kind of this future. I need to get the result from those async results. So I'm going to do that by essentially, again, just doing a loop through all the async results, and you've got to call the get method. The get method will return those results. There's things you can do by putting timeouts and things like that. I'm keeping this video simple and giving you basically what you're going to be able to use 80% of the time, or it will cover 80 to 90% of your use cases. So I'm going to make a list comprehension. To do this loop, I'm going to loop for result in async results. And what do I want for every result? I need to call the get method. That's going to get the actual returned value that func returned, right? Result.get. And then all I'm going to do here, I'm going to print, just to show you that we actually do get an output, I'm going to print results 0, like so. Okay, and then I'm just going to take the same code as before to run this, right? So we've got the seed, I've got the job size, the pool size, and we'll set the pool size equal to 1, okay? And then let's go ahead and run this. And again, I'll pause the video. I won't bother looking at the CPU usage anymore. We've seen how that works. So I can close that off. And let's just go ahead and run it. And I will pause the video and come back when it's done, because again, this is going to take a little while to run. All right, so it finished running, it printed out all our prime numbers, and it took 55 seconds to run. So in line with what we had before, right? No difference. I think we had 57 seconds before. So I'm now going to, oh, and I just want to show you before all that the function was indeed printing out all the arguments that we were passing. And I've lost it here. So, well, let's go ahead, set the pool size to 8. Let's run it. And you'll see that, right, it's got all these different values, A, B, upper bound, and so on. One thing as well that you'll notice is that the jobs are getting kicked off in sequence, right? Again, I probably went past the buffer size that I have here. Now, the reason why they're getting kicked off in sequence is that we essentially kick them off in sequence here. Now, they may not finish in the same sequence, right? Because they're going to take different amounts of time to compute since we're computing we have different upper bounds, right? We've got a random integer between 1 million and 10 million. That's our upper bound for the sieve. So it's going to finish at different time periods. But as you can see, we went down to 10 seconds. So this is no different than before. Really what I wanted to show you here is how we can use apply async to essentially be able to pass both positionals and named arguments, or even if it's just named arguments, in which case your args, would be empty. You'd have nothing there. You'd just have your keywords. So this is, probably the better way of doing it rather than trying to write wrapper functions, and that's kind of convoluted and not necessary. All right, so that's it. Hopefully you've enjoyed this video. And again, everything is in the notebook that is in the repo, right? So I have everything here, and I have those 3 examples as well. All right, so I kind of scratched the other options that you have for multiprocessing. It can get really complicated, and it gets complicated really fast. But as I said, when I'm working in kind of more production environments, we need more scalability than what just a single machine provides. So I rarely use multiprocessing because of that. But sometimes when I'm writing code for my own machine, or I just, need something simple, then I will certainly use multiprocessing if I want to speed things up when it's a CPU-bound workload. Obviously, if it's an IO-bound workload, I'm going to use async or potentially threading, depending, sometimes threading is a lot simpler to use than async, but it has its, pitfalls and caveats as well. All right, thanks for watching.